Given a monocular video sequence captured in the wild with dynamic distractors, WildGS-SLAM accurately tracks the camera trajectory and reconstructs a 3D Gaussian map on the fly for static elements, effectively removing all dynamic components. Note that we also include the final rendering results after the final global BA and mapping refinement. So, why do we build this SLAM system? Most SLAM methods assume static scenes. Here, we demonstrate the performance of state-of-the-art classical SLAM method DSO and the SOTA Gaussian splatting SLAM method MonoGS on static environments. However, the presence of dynamic objects can disrupt feature matching and photometric consistency, causing substantial tracking drift. As can be seen, the performance of both methods deteriorates significantly in dynamic environments. Here we explore two well-known classical methods for handling dynamic environments in SLAM. The first is DynaSLAM. This method is designed to handle dynamic environments effectively and works with monocular input. However, it relies on semantic segmentation for detecting moving objects and doesn't support dense mapping. Next is Refusion. Unlike DynaSLAM, Refusion handled dynamic environments using a purely geometric approach. While it avoids the need for semantic segmentation, it requires input from a depth sensor, which limits its use in monocular settings. Recently, several neural implicit dynamic SLAM methods have been proposed. DDN-SLAM can handle dynamic environments and supports monocular input. However, it relies on object detection with feature reprojection error check and has not been open-sourced. Similarly, Dynamon also supports dynamic environments and monocular input. However, it depends on semantic segmentation combined with optical flow-based motion masks. Our WildGS-SLAM efficiently handles dynamic environments using only monocular input. It operates without the need for any class priors, object detection, or semantic segmentation. Additionally, it enables online tracking and dense reconstruction. Here is the pipeline of our method. WildGS-SLAM takes a sequence of RGB images as input. Our method is more robust to the dynamic environment due to the uncertainty estimation module, where a pre-trained DynoV2 model is first used to extract the image features. An uncertainty MLP then utilizes the extracted features to predict per-pixel uncertainty. During the tracking, we leverage the predicted uncertainty as the weight in the dense bundle adjustment layer to mitigate the impact of dynamic distractors. We further use monocular metric depth to facilitate the pose estimation. In the mapping module, we incrementally map the scanned static environment as 3D Gaussians. Given keyframe poses estimated in the tracking module, we first render RGB images and depth from the 3D Gaussian map. The predicted uncertainty is incorporated into the rendering loss to update 3D Gaussian map. Moreover, the uncertainty loss is computed in parallel. Note that the uncertainty MLP and the 3D Gaussians are optimized independently, as illustrated by the gradient flow in the gray dashed line. To further assess performance in unconstrained, real-world settings, we introduce the WildSLAM dataset, comprising two subsets, WildSLAM Mocap and WildSLAM iPhone. The WildSLAM Mocap dataset includes 10 RGBD sequences featuring various moving objects as distractors, specifically designed for dynamic SLAM benchmarking. The sequences are recorded with an Intel RealSense D455 camera with a fixed exposure time. Although WildGS-SLAM works with only monocular inputs, depth images are also included in the dataset to support the evaluation of other RGBD baselines or future research. The room is equipped with an OptiTrack motion capture system, providing ground truth camera trajectories. To further assess performance in more unconstrained, real-world scenarios, we collected the WildSLAM iPhone dataset, which comprises 7 non-staged RGB sequences recorded with an iPhone 14 Pro. These sequences comprise 4 outdoor and 3 indoor scenes, showcasing a variety of daily life activities such as strolling along streets, shopping, navigating a parking garage, and exploring an art museum. Since ground truth trajectories are not available for this dataset, it is used solely for qualitative experiments. Now let's look at some results. Here we present the results on the ball sequence from the WildSLAM Mocap dataset. We visualize the uncertainty map in the top right corner. In the bottom right, we plot the 2D camera trajectory alongside the ground truth, with the error color mapped. Blue indicates low error, while red represents high error. Our method demonstrates low tracking error while effectively removing distractors in the dynamic environment. Here, we present the comparison results for the umbrella sequence from the WildGS-SLAM Mocap dataset. We compare our method against MonoGS and SLAM. Both baseline methods exhibit significant tracking errors as shown in the trajectory plot. Moreover, they suffer from blurry rendering artifacts, primarily because they do not explicitly account for dynamic environments. Here, we in addition showcase the comparison results for the stone sequence from the WildGS-SLAM Mocap dataset. Similar to the umbrella sequence, both MonoGS and SLAM show significant tracking errors and blurry rendering artifacts due to their lack of explicit handling of dynamic environments. In contrast, our WildGS-SLAM achieves accurate tracking and produces artifact-free, realistic renderings of the static scene, enabled by our uncertainty-aware mapping approach. We further evaluate our method on the WildGS-SLAM iPhone dataset. Since ground truth trajectories are unavailable, we focus on qualitative results. Here, we present the street sequence, where our approach outperforms MonoGS and SLAM by achieving significantly improved rendering quality while having accurate uncertainty predictions, even when handling challenging elements such as a transparent glass window. In addition, we capture the tower sequence inside an art museum, successfully reconstructing the highly detailed artwork despite the presence of distractors. That's all. The code and dataset will be made publicly available. Thanks for watching.